Hey there. So we are on a problem to sum. It's a very famous problem and a very simple problem. Apparently, it's the number one problem on Leetcode. Let's see. Let's take a look at the problem. So we are given an array of integers. We are calling it nums. There is an integer target. Okay, we need to reach this target by adding up the numbers from nums. So if this is the num, we need to add two numbers and we want to reach this target. There is one very important piece of information, exactly one solution. Okay, and that plays an important role in the implementation of this solution. Also, you cannot use the same element twice. So if I'm at 2, I cannot use 2 again. But if there is 2 over here, I can use that too. The answer can be returned in any order. So we need to return the indexes. We can return them in any order. So either 0, 1 or 1, 0. If we look at the problem number 1, we have nums 2, 7, 11, 15 need to reach the target 9. So what would be the solution? We can add this and we have 9, 2 plus 7. So we have a solution over here. What would be a very simple naive solution to the problem? Let's take a look at that. You have 2, 7, 11, and 15. We want to reach a target of 9. So take a pointer over here, I. Since we can't take the element twice, take a pointer over here, j. Add these two numbers. Now, let's say it was not 9 because we would get an answer on the first try itself. Let's say we were looking for 18. So if you add these numbers, 2 and 7, that is 9, not equals to 18. So we move j to this position. J is over here. I is over here. So we say 11 plus 2 is 13, not 18. And we keep going. It's 17. J is over here. It's 17, not equal to 18. So now I moves a step forward to 7. I is at 7 and J would start at 11. We would not start before because 2 and 7 are already considered. So move J to the next position after I and take the sum. 7 plus 11, that is 18, which is equal to target. So we found the solution. And what would we return? This is index number 1, index number 2. So we return 1 or 2. Or we can return 2 or 1. Both are correct. This, of course, is a naive solution. It has a time complexity of n square. You are moving I in every position and you are moving j in every position. So that would be an n square algorithm. If you look at the bottom of the problem, it clearly states that we need an algorithm better than O of n square. Now take a look at the clever solution. We have 2, 7, 11, and 15. We want to reach 9. How about we do not go through every element, but instead search for an element which would make 9? How about we do something like in this situation, if I subtract 2 from 9, 9 minus 2, 7, then I can say that I want to see if 7 exists in my array. If it exists, I have a solution, which it does. Let's say I had the same array and I wanted 18. Then in the first try, I would put a pointer over here, I pointing to 2, and I can say 18 minus 2 is 16. Is 16 present? No, so this cannot be a solution. Let's go to 7. 18 minus 7 would be 11. Do I have 11 present? And the answer is yes. So we have a solution over here. This time, we would not travel through every element twice, but just once. We would move the pointer forward. We would use extra space to store the location of these numbers. Basically, the time complexity would be O of n, and the space complexity would be O of n. Now we can take a quick look at the code. First of all, I need a map to store the values corresponding to their index. Let's call it values. It's a map. It will be a map of value and its index. Let's fill this map. So for I in range 0 to length of nums, I want to fill this with nums equals to the index. Next thing, I would traverse through the nums array and subtract the value of nums at that position from target. And whatever value I get, I would try to search it in the array. If I find it, I have a solution. So for, let's say for I in range 0 to length of nums, I can say what I want to look at. Look equals to target minus nums at that location. So if the look, I find this look, if look in values at the same time, the I is not equals to inside the values look, then I want to return this as a solution. So the solution would be I comma values look. And since we have one solution, we don't have to worry about anything else. So let's try to run this. It's passing. Let's submit. So we have a solution. Can we further improve this algorithm? Because you might have noticed something. What if this array is really big, 10,000 elements, which we can actually go? And the solution is in the beginning. Then you are unnecessarily spending time traversing every other thing in this first iteration. It loops through all 10,000 elements and consume a lot of resources. Can we have a single map? And the answer is yes. What we would do is we would implement a single pass algorithm. Instead of storing these values in the map in the initialization phase, we would just have this one loop and we would look backwards. So right now we were subtracting the first element from target. We were looking at the look value in the forward direction. We would no longer do that. We would look at that in the backward direction, an element that we have already seen. Let's see how we do that over here. I would remove this loop. There is no need to do that so many times. I would remove all of this. So I have a look value. What I would do is, do I find the look value? If look in values, if we have this value in the values, then I would return I comma values of look, and this should be inside an array. Otherwise, in the else condition, I would add this look, or I would add this nums of I in values. So values nums of I equals to the index. That's how I would proceed. Let's submit this code. We do not have any error. It's passing with, it beats 100%. It beats everybody.